Welcome back, dear students. So already in the previous session we have discussed the principle behind pyrolysis and different applications of products of pyrolysis, etc. So in this we will discuss about the some of the basic designs of pyrolysis reactors. So and if you look at the important pyrolysis reactors, they are: first one we have fixed bed reactor, followed by fluidized bed reactor and circulating fluidized bed reactor, ablative reactor, the rotating cone type reactor, and vacuum pyrolysis reactor. And the last one is the auger or screw type reactor. So these are the some of the important reactors used for pyrolysis in different applications. So we will see one by one. First we will see the fixed bed reactors. So this is the design of a fixed bed reactor. So similar to a fixed bed gasifier and fixed bed combustor, etc. Similar to that, but except we have a external heat supply here. So we will have a inert gas is required because the pyrolysis is carried out in absence of oxygen. We have to purge the reactor with inert gas. So normally nitrogen will be mostly used. So that gas will be passed through this fixed bed continuously, and these are the distributors. And we will have a heated zone. In this particular session is heated to a pyrolysis temperature with the help of some external source, and biomass will be fed through this, and the product, the gas, liquid, etc. will go through this, while these solid char we can take it from the bottom. So this is a fixed bed reactor, and its advantages are simple and reliable design. It's very simple design, and any particle size, that is another advantage. We can use biomass of any particle size for this type of reactors. But the problem is this is suitable only for small scale laboratory type investigations. So we cannot industrialize or commercialize this type of reactor for large scale pyrolysis. And its oil yield is also less. If you take the bio oil yield, it is around 35 to 50%. So the total pyrolysis product, in that the bio oil will be only 35 to 50%. The remaining will be the gas and char. And why we are not able to commercialize these fixed bed reactors are which is having the following problems. That is, first one, we have a maintenance problem of clogging of the reactor bed with char and tar compounds. So here you can see this is a reactor bed. So as we continuously use this type of reactors, this bed will be clogged with char and tar compounds, and also there is an increased resistance of gas. So as this is get clogged, it will be very difficult to pass this purging gas through this. So there will be an increased resistance of sweeping gas. And another problem is it is having a long solid residence time. So the residence time of the solid will be more. So due to these reasons, it's not advisable to commercialize this type of fixed bed reactors. And when we have the fluidized bed reactor, and normally it is a bubbling fluidized bed reactor, BFB, because we have a circulating fluidized bed reactor coming in the next chapter. So here we have fluidized bed reactor or bubbling fluidized bed reactor. So in this we can see we have already understood the concept of fluidized bed. We will be fluidizing the bed, and mostly the bed material will be sand, etc. So we are using a fluidizing gas for making this bed into fluidized state, and biomass will be fed at the bottom, not at the top like fixed bed. Here it will be at the bottom, so that our biomass also will be in the fluidized state, and the gas will be taken outside, right? The gas and char etc. that will go through this outlet, and this is the most documented and commercially available reactor among all the pyrolysis. So if you compare all the 6 or 7 pyrolysis reactors, in that best suited for large scale pyrolysis and commercialization is this one, that is a bubbling fluidized bed reactor. And here we are creating a hydrodynamically stable bed of smaller size biomass particles with the help of a inert fluidizing gas. So here the velocity of our inert fluidizing gas is important, and our biomass as well as the bed material will be in a fluidized state with the help of this fluidized gas. And another important thing is in this type of reactors we have to be only suitable for biomass particle of this range, that is 0.5 to 2 millimeter only. So smaller particle size is required for this type of fluidized bed reactors. And normally sand or other material can be used for increasing the abrasion of biomass particles as the bed material. And it has the advantage of fluidized state, that is it's having a uniform temperature distribution and high heat transfer rate compared to other reactors. And we will get a high quality bio yield. It's around 70 to 75% bio yield is possible, and maintenance also is very less. And already we have talked, this is very much suitable for large scale operations. So these are the advantages of fluidized bubbling fluidized reactor. But the problem is the biomass size should be this much less, that is it's suitable for particle size of 2 millimeter or less. So that is the only disadvantage of this type of reactors. Now we have discussed this circulating fluidized bed gasifier etc. So similar to here, this one also we have the circulated fluidized bed pyrolysis reactor. So here we will be using more velocity. As for fluidized gas we will be using more velocity, so the fluidized and the particles moving through the gas will be going through a separator here, and that will be this separator here, and this separator will separate the char and sand, and it will be returned to here, and we will combust this char for as a source of this heat source. We can combust this char in the second reactor, and these are connected. So that is the idea of circulating fluidized bed reactor. So in contrast to the bubbling reactor, these having low heat transfer, but we are using a high gas velocities for better char attrition. And again the important thing is we are recirculating, so we will be using high fluidized velocity here, but as a result this char and other sand etc will be carried away with this gas, and it is separated in this separator, and char is returned here, and the combustion of char and sand etc is used as a heat source. So this is a complex system compared to the bubbling fluidized reactor. This you can see this is a complex system due to the separator and this second reactor etc. And here we can use a maximum particle size of 6 millimeter, and not like a 2 millimeter. Here we can use a particle size of around 6 millimeter, and the bio oil yield is 70 to 75%. So we can use a more bio oil yield very near to the normal gas fluidized bed reactor. But the major problem is this is the high gas velocity. Due to the high gas velocity, so even though it's the heat is generated self generated, due to the high gas velocity, the mass, the amount of this biomass that can be reused in this. The throughput volume is not that is a problem of this reactor. With this high gas velocity, we have this high volume also required in this type of reactors, and we are reheating this sand particle with the combustion of char, but that may be lead to the ash buildup in the circulating bed. So as we are combusting this char for the required heat, some ash will be formed, and that ash buildup will be a problem with the continuous use. So these are some disadvantage of these circulating fluidized bed reactors. And this buildup, the ash buildup can use finally result in the cracking, catalytic cracking, that may be led to the decrease in the volatile matter of the bio oil. So one of the disadvantage of this is this ash formation, and this ash formation will lead in the decrease in volatile matter of the bio oil produced. So these are due to this is not suitable for large scale, maybe a laboratory scale only due to these disadvantages. This is a complex system, and this heat generation, ash formation, etc. is not suitable for large scale. We have an ablative reactor. What is an ablative reactor? We will have a rotating disc like this, and this is a high temperature disc with the help of some source. This rotating disc will be kept at a high temperature, and we will keep the biomass on this disc, and some pressure is applied. So that is the principle of ablative reactor. We have a rotating disc rotating at a particular speed, and that disc will be at a high temperature with the help of some external source, whether electric or some with the help of some gas, etc. And we will place the biomass here, and some pressure is applied. We can convert that into char and other product of pyrolysis. So here we have to with simultaneous heating and renewal of biomass is required with the help of a rotating disc. So here the main thing is the heat transfer is solid to solid compared to other reactors. So we have discussed 3 reactors so far. That is mainly fluidized bed, circulating fluidized bed, and fixed bed. So all that reactors, we have a solid to gas heat transfer occurs, other than solid to solid heat transfer. But here we have only the solid to solid heat transfer. No gas or other heat transfer occurs in this type of reactors. And this is suitable only small scale, because we have to continuously remove the biomass after it is converted to char manually. So this is not suitable for large scale, and also high speed of rotation is required, and we have to, as the speed increases, we have to increase the pressure applied on this biomass due to the sliding friction. So this is only a typical particular application only. This type of reactors may be not suitable for a large scale biomass, biochar production, etc. So then we have a rotating cone reactor. So in this we are having a rotating cone, rotating cone like this, and we will pass the biomass particle as well as the sand. So by the centrifugal action, this will be mixed, and this will be converted into different products. So in a rotating cone pyrolysis, the biomass is filled in a high speed in a rotating cone along with hot sand, and in the absence of oxygen. And the high speed causes the proper mixing of biomass and sand particles, and better heat transfer and surface abrasion of biomass also takes place. And by this combined action of the pyrolysis achieved by the help of combined action of fluid mixing and this mechanical action. So here the main source of heat is the hot sand. So that hot sand mixed with the biomass, and that abrasion will cause the pyrolysis. And the energy required can be met by the char combustion. Here also, if you want, you can obtain the energy. The hot sand can be obtained with the help of the combustion of char. So this is we can use as a self heat generating autonomous system for energy input. And here we can approximately 70% bio-oil yield can be achieved. And the advantage is here we are not using any inert gas, nitrogen etc. are not required. So that is the advantage. We are not like if in the fixed bed and fluidized reactors we have to supply this nitrogen gas continuously. But here there is no requirement of that inert gas. But this is not suitable for some large scale application because this char how we are not char get obtained is very less, and also here we can see the 75% is oil, bio oil, so char obtained will be very less, and that char also we are using for the heat generation or heating the sand etc. So this is not suitable for agriculture purpose. So if you are looking for a biochar oriented application, this is not suitable. The biochar already we know is used for carbon dioxide sequestration and soil enhancement etc. But that is not suitable for this type of reactors. And another one is we have vacuum pyrolysis reactor. So here we are creating a vacuum, a heated vacuum is created and biomass is supplied, and we will obtain the products. So vacuum pyrolysis, the advantage is here also we are not using any carrier gas, inert gas is required just like the previous system, and we will get a good control over vapor residence time, and we can use a very large size biomass also. So in this vacuum reactor the one advantage is we can use very large sized biomass, not like the fluidized bed reactors. And also the rapid volatilization of this reduced pressure. So we are passing the biomass in a reduced pressure region, so it will help in the rapid volatilization, and we can therefore the heat input will be very less. So that is the advantage of this vacuum pyrolysis. Already we are supplying biomass in a region where the pressure is very less, so it will be very easily volatilized, volatile components easily volatilized, and the pyrolysis temperature required is less, hence the heat input also is very less. But it's also not useful for large scale application because it's a low heat transfer, mass transfer, and equipment size is very large, therefore high capital investment is required. So this is also not suitable for any large scale production. And continuous operation of vacuum pyrolysis also requires some special input mechanism. So the continuously, if you have to maintain a system in a vacuum, that will be very difficult. So these are the problems associated with these vacuum pyrolysis reactors. And finally we have an Auger reactor. So Auger is a screw type reactor which is already we are using it for convey traveling products from one place to other in storage and handling systems. We are using screw conveyors. So similar to that, the main part of this Auger type reactor is a screw rotating at a particular speed, and biomass and hot sand will be supplied to the screw, and we will get the gas and the other liquid through this, and char and sand will be collected here. So here the auger is used to transport the biomass through a heated pyrolysis zone, and the biomass temperature is raised to the desired pyrolysis temperature through the heated zone with the help of auger rotation speed. So here the design of auger is very important, like the rotation speed of the auger, the pitch and diameter of the auger, particle size etc. are very important, because it determines the product of the pyrolysis. And the auger pyrolysis is having many strengths. It's very simple and compact, and here also we does not require any carrier gas, an easy operation of separation of. So here we can see very easily the biochar and this oil are separated very easily, and energy requirement is also less. But only at disadvantage is having a moving part, so the continuously moving screw is required. So mainly it will have some wear and tear after frequent use. But this is mostly used in large scale also in today, because the development in material science and machining, we have precise machining options available today, so we can overcome these challenges of wear and tear, etc. So this is also suitable for large scale production of biochar and other bio oil, etc. So if you look at the overall comparison of these reactors, this is a very good comparison of reactors, yield, etc. So first we have fixed bed reactor, but it is only used, the fixed bed reactor main advantage is we can use the large biomass size, we can use this large biomass we can use, and also any type of biomass we can use. The variability of biomass is high, but scale, if you want to scale up this fixed bed reactors, it is very difficult, and its operation is very medium. And if you look at the fluidized bed, its advantage is, its problem is you can use only small particle size. Already we have seen 2 millimeter or less, and also the biomass variation is very less. We have to be constricted to a few biomass only. But advantage is we can use it is very much suitable for large scale applications. Scale up is very easy. And recirculating bed is again a particle we can use somewhat greater, that's a medium size, 6 millimeter in that range, and biomass variability is again low and is not suitable for large scale production. And then we have a rotating cone type. Here also the biomass variability is high, scale up is somewhat medium, and if you compare, inert gas is not required, it's very low or sometimes not at all required. Then we have ablative reactor, but it is very complex. We can see its operation is complex, but we can use large biomass with high variations, and it's not suitable for scale up. And inert gas is not required that much. And then we have screw type reactors or Auger reactor, though here it's very easy, its operation is low, complexity is low, a medium size biomass we can use, and it's very much suitable for large scale. So in this large scale pyrolysis is suitable for only two, that is, one is fluidized bed, another one is the Auger reactor. And here also the inert gas is not at all required. Then we have vacuum reactor. Here also we can use very large biomass, but this is not suitable for scale up. So this is the overall comparison of these reactors is obtained from this particular journal. So this will give you an overall view of which one is suitable for large scale, which is used for large particle biomass, which is operation is very easy, etc. So with this we are stopping this, and we will continue with another session. Thank you.